Hello all. So in last lecture we finished deriving the equation for this periodogram. So basically this is called periodogram, right? And in this lecture we will be starting with the consistency of estimator. So given a estimator or periodogram, how we can characterize this periodogram? That is based on which parameters we can say that whether the given estimator is good or bad. So we will see that bias and variance and eventually the mean square error is the thing which is very useful in order to derive this consistency of estimator. So let's begin. So this is a periodogram, and one important thing about this periodogram is that, as we already know, that periodogram is a candidate estimator of true spectrum, right? Because this is the estimate. So we can say that is a candidate estimator of our true spectrum. And throughout our lecture series, we will be denoting the true spectrum by Cxx of e power j omega. Right? So we will be using this notation Cxx of e power j omega. So given process, random process x of n in discrete domain, we want what is our target in this entire lecture series? The target is that we want its spectral estimate. But since this is a random process, we can't get actual value, that is Cxx of e power j omega, but we get the estimated value. And this estimated value is given by this periodogram, right? So now let's continue with our actual aim of this lecture, that is consistency. So as I already said, that bias and variance, so eventually I will go to mean square error. So firstly let me introduce what is bias and what is variance, right? So let me write the entire thing, that bias and variance are two basic measures often used to characterize the performance of the spectral estimate. So performance of the spectrum estimator. So for optimal estimator, we need some optimal criteria, and that criteria is nothing but the mean square error. So that we will derive eventually, that how mean square error is related to is a function of bias and variance. So we will be deriving this thing. Okay. So basically it's nothing but mean square error is the combination of both this criteria. Okay, which is more optimal. That's it. So let's say the true spectrum is given by Cxx of e power j omega, right? So I am now defining MSC, and I will solve this MSC, that is mean square error equation, in order to define bias and variance. So at the end we will be having bias term and one variance term that we will see. So basically this is our true spectrum. So what is MSC? Now I am defining this is true spectrum, and this is its expected value, let's say denoted by cap. So it is expected value of its spectrum, right? Mean square error means, first this is the error, true minus expected value. This will be the error, but it is mean squared. So first it is squared, and then we are taking the mean. Let's say we have n number of sample observations. So this is defined as mean square error, right? So now let's try to derive it further in terms of bias and variance, right? So basically, firstly what I will do is that in order to take the mean, as we already know that mean is nothing but the expectation operator. So I am not writing the mean, but I am writing the expectation operator, and that will be good enough. So let me just write that the expected value of the true minus original and its squared is nothing but our mean square error. Now what I am doing is that I am simply expanding it. Okay, this is a minus b whole square, right? So I am just expanding it, so I can write e of Cxx of e power j omega square minus 2 cxx of e power j omega and cxx of cap of e power j omega, and at the end plus cxx of e power j omega and its square and expectation. And since expectation is linear operator, we can give expectation operator to all individual terms. So let's try to do this here. So basically we are left with expected value of cxx of, let me just go to previous page, cxx of e power j omega square. So let's write e power j omega square, then we will be having minus twice, so it will be minus 2 times of expected value of cxx of e power j omega and cxx hat of e power j omega, right? So it's entire expected value, and at the end we are having expected value of cxx cap of e power j omega and its square, of course. So we are just giving expectation to individual terms. Now since this is a deterministic, this is not the estimated one, okay, so this is not the random process, but it is the deterministic spectrum, and that's why the expectation operator of any deterministic thing is itself. So here if we write e, or if we won't write, it won't make any sense. So just I am not writing this e over here, right, because this is a deterministic term. Similarly we can follow that here you can take cxx of e power j omega outside and just give expectation operator to this, okay, and that is okay, right? So I am just writing the same thing, and here it will be for the entire term because this is the estimate, right? So let's just rearrange the terms. I am just writing this last term first. So I am writing cxx of cap of e power j omega square minus twice expectation operator of, I am just writing expectation, inside the expectation just the cap and nothing else. So cxx I am taking outside, right, and at the end the last term, which is nothing but simple cxx e power j omega whole square. I just rearrange the terms. Now what I am doing is that I am just adding and subtracting something. So I am just adding expectation of cxx of e power j omega square, okay, so I am just adding the square of it, and obviously if I added I need to subtract it. So I am here adding, then I need to subtract it as well. So I am just subtracting. So subtracting the same term square. I am just adding and subtracting, that's it. Okay, so let's see what we'll get now. So first term was e of cxx cap of e power j omega square, and what we added is that expectation of cxx of e power j omega the whole square, right? The squared, actually we added this square term, okay, let me just check what I wrote here. So it basically the square of this thing, okay, just don't get confused. The square is not for cxx of e power j omega, it is the square of the expectation. So basically we are taking expectation twice, or we can say first we will take expectation and then we will again take expectation and we will multiply them. Okay, so I hope it is clear that it is expectation square of this, right? Okay, so mind about the notation, these two are different thing. Here the square is for the spectrum, whereas here the square is for the expectation operator, right? So the cap, so I just took the last term from here to with this term, okay. Similarly the rest of the terms, that is this plus, let me change the color, this term, then this term, this entire term, and what we are left with is this will form a simple a square minus 2ab plus b square, right? So this will be our a and this will be b. So a square minus 2ab, this is minus 2ab, and this will be b square. this will be our term b square. So this will give a minus b square. So what is our a? This, and what is our b? Is this. So I am just writing over here that this will give expectation of cxx of e power j omega cap minus cxx, the original one, and its square. Okay, so we will get the square of this entire term. So this is our first term, this is our second term, and it's squared, that we will get. So now we are ready to define our variance. So basically we know that the taking square of the expected value, okay, and this is let me just speak once again that this is taking the square of the spectrum and then taking the expected value, and this is the taking the expectation twice, that is, it is square of expectation. Okay, so basically this term is called variance of cxx of e power j omega. This is the definition of variance, cap, of course. So basically the first term will be the variance of cxx cap of e power j omega, and the second term is called bias. So you can see that what is bias? Bias is the difference between, from this mathematical equation you can say that bias is nothing but the difference between the expected value and true value of any quantity. So here the bias will be of this quantity, right? So it is called cxx cap of e power j omega, but obviously it will be squared. So whole square, or you can write bias square of this. Okay, so we derived MSc in terms of variance and bias, right? And we know that this is, at the end, it is the error, right? So as the number of samples tends to infinity, this MSc should also tends to 0, right? Because we want at the end the error should be minimum. So if we observe more and more number of samples, why we get estimate? Because we are having a finite length of sample. So if we get theoretically infinite number of samples, that is from minus infinity to plus infinity, because we are assuming that n is tending, and this is nothing but the asymptotic behavior. So asymptotic behavior occurs when we observe any quantity at its farthest value, that is infinity. So in order to have MSc to 0, our variance should also tends to 0 and our bias should also tends to 0, right? So we got one definition of our consistency of estimator, that the estimator, let me write this, that what is called consistency now. So let me just write consistency. So consistency of estimator is given by, let's say, if the variance and bias of an estimator becomes 0 or tends to 0 as the signal length, or our process length, or our x of n, that is our process, sampled process from the original process x of t. All these are WSS process that we already assume. So as the signal length n tends to infinity, then the estimator is called consistent estimator. Correct? So now let's, as we already defined our periodogram, right? So let's try to find its bias and variance. So bias already includes the expectation term. So basically we will be finding its mean, that is expectation of our periodogram, then its variance. And after finding that, let's conclude that whether a periodogram is a consistent estimator or not based on this criteria. So we will be doing the same thing in our next video, right? So basically the next video will be about finding the mean and variance of our periodogram that we already derived in our last lecture. So in this lecture basically we just had one criteria, that's it. So there are other criteria as well, like frequency, resolution and all, but that we will be seeing one by one after we will be seeing the examples. So that's it about this. Thank you.